this is my final project for robotic manipulation. In this project, I'm exploring how natural language can be used to enhance the perception capabilities of robots. I'm going to focus on two-dimensional tabletop pick and place tasks. So you can imagine the task looking like something as shown in the figure, that there are a few objects placed on the table and we are saying in a natural language format to pick some objects and place them at some location. Now, an advantage over here is that these kind of instructions are very generalized and they let us focus on the important things and not on the background. So the pipeline that I have created is that the robot views the tabletop scene and it sends this 2D image to a vision language model, which is a neural network that generates the pick and place locations. And then for motion planning, the robot can use these two locations to generate a trajectory between them. However, the main focus of the project will be to understand the properties of the vision language model. So I set out with a very simple idea that we can take the scene and pass it through a pre-trained residual network, which is a state-of-the-art image embedding model. And similarly for text, I took the BERT transformer model and I generated the two embeddings. And I passed them through a linear neural network to generate pick and place coordinates. This did not work out very well because the embeddings generated by ResNet and BERT were not correlated to each other, as the weights were not trained for image and text together. So we are able to see pick and place locations generated in the red in the figure on the top right, but they have no relation to where our objects are. So one hypothesis I had about this, as I said, was that the weights are not trained together. So OpenAI has this really interesting model called CLIP, which uses contrastive learning to learn these two weights together. So I took the pre-trained weights from that model, and I was able to get better results with that. As you can see on the figure in the top right, the model is able to correctly predict the direction of movement, but the points are very close to each other. For this, my hypothesis was that the linear model is very simple and it does not capture the spatial information which is so critical to generating the pick and place locations. So I replaced the linear model with more complicated convolutional decoders. So in the next step, I used the clip image processor, but in a different way. I did not use the full clip image processor, but only a few layers in which they generate a spatial image embedding where the spatial information has not been lost yet. The text still goes through the clip language processor, which generates the language embedding. And using these two, I pass it through multiple convolutional layers, which finally end up generating uh, an embedding which is of the same dimension as the scene, and each value in the result is like a probability that this pixel is the pick or the place location, and then we can take the maximum of them to generate pick and place locations. So this model worked much better, and as we can see in the figure on the top right, that if we have two objects like the blue and the black square, the model has been able to predict the pick and place locations much better in the red dots. So through this project, I learned a lot about the properties of such deep vision language models,